Hello guys, welcome back. This is lecture 20 of the lecture series Signals and Systems. In this video, we'll be learning about the duality property of discrete time Fourier series and discrete time Fourier transform, and we'll discuss some basic discrete time Fourier transform pairs, and finally we'll see systems characterized by linear constant coefficient difference equations. So let's get started. So up until now we have seen 4 transformations, right? Of course, excluding Laplace transform analysis. In the Fourier domain only, we have seen 4 transformations. The first is the continuous time Fourier series. Second, we saw the continuous time Fourier transform. So this is Fourier series is for periodic signals and Fourier transform is for aperiodic signals. And we also had the discrete time Fourier series and discrete time Fourier transform. And these are the synthesis and analysis equation for each of them. And we also observed the duality relationship in the continuous time Fourier transform. Why? Because both were of similar nature, right? As you can observe here, you have an integral in both cases and your integral is going from minus infinity to infinity. But if you see in all other cases, in the continuous time Fourier series, you have a summation here and an integral here. So there is no relation between the synthesis and analysis, like no direct relation, right? So that's why we were, until up to now, we were only observing the duality in the continuous time Fourier transform. So let us just first try to review it, okay? So duality in continuous time Fourier transform. So this is a synthesis equation. X of j omega e power j omega t d omega, and this was our analysis equation, right? Minus infinity to infinity x of t e power minus j omega t dt. So duality, what did we observe? If let's say my x of t is of a square pulse, then we observed a signal of the form of let's say x of j omega sine omega by omega form, correct? Which will be like this. So what it means is, if I have a time domain signal which is of the form of sine t by t, then it means that my frequency domain will be again like a square pulse or window, whatever you call it as. So this is versus time. This is versus frequency. Of course, you can call it x prime, xj of t. But what it actually means is, if you give this x of t, this capital X is corresponding to this function, you will get some constant times some x of some bn, correct? Bt, sorry. Right? Something of this form you will get, and you got this a and b. You found out. So we'll try to find it again. So if my x of t has continuous time Fourier transform x of j omega, then I need to find what does my x of t have the continuous time Fourier transform as. So we'll pick one equation. Let's say my x of t is equal to 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega. So now what I'll do, I'll replace my omega terms with t variable and t with omega. So this I can either do it in 2 steps, where I replace omega with some other theta and then convert to t, and similarly t I can replace with some other variable and finally convert to omega. But instead of that, I am doing it in 1 step. So what will I get? I'll get x of omega equal to 1 over 2 pi integral minus infinity to infinity x of jt e power j t omega dt, right? So again, my x of jt is identical to x of t. It is just a convention. We also write the j term. Otherwise, we can write x of t. And where does this x of j omega convention comes from? It comes from x of s, right? And you substitute s equal to sigma plus j omega. That is where it comes from. So if I replace with x of t, I can write it as x of omega equal to 1 over 2 pi integral minus infinity to infinity x of t e power j, I'll just exchange them. So dt. So now I want to find x of t continuous time Fourier transform. So if this is something of the form of my continuous time Fourier series, let's say, where is it? Yeah, this equation, I have this, and here I have minus j omega t. So if somehow I'm able to bring it to minus j omega t, then I can say whatever is present here and its continuous time Fourier transform will be whatever is present here. Okay, so I'll try to bring this to minus j omega t. So what I have to do, x of t anyway I want, because that is what is in my left hand side. So I will not modify t, I'll modify omega. So I'll write omega to minus omega. So then what I'll get x of minus omega equal to 1 over 2 pi integral minus infinity to infinity x of t e power minus j omega t dt. So now if you see, this is of what form I expect, but also I have 1 over 2 pi factor there which is not present here. So I'll just bring it here. So 2 pi x of minus omega equal to integral minus infinity to infinity x of t e power minus j omega t dt. So now it is of the form of my continuous time Fourier transform. So what is my Fourier transform of x of t? It is nothing but 2 pi x of minus omega. So that is what I'll write here. So 2 pi x of minus omega. So whatever is transforming from here to here, right, it will be nothing but 2 pi into x of minus omega. Earlier I had written it as t, which was wrong because my variable here becomes omega. So we have a constant factor multiplying x of t, and also the variable is reversed. So since this square pulse was an even function, we did not notice that reversal. Okay. So this is duality in continuous time Fourier transform. So let us also look for something similar in the discrete time domain. Okay. So if you see the discrete time Fourier series, you have both having the summation terms and both are summing over n. So we can say that these two also form a duality relationship. So that is what we will see next. So next is your duality in discrete time Fourier series. So again, first let me write out both the equations, my synthesis and analysis equation. So what is my synthesis equation? X of n equal to summation over ak, right? So x of n equal to sum k over n ak e power j k into 2 pi over n into n. And my ak, instead of writing it as ak, I'll just write it here so that it is easy for you to understand. So I have 1 over n sum of n over n x of n e power minus jk 2 pi over n into n. So first let me say that my x of n as a discrete time Fourier series coefficients ak's, I'll write it as a of k. Then I need to find if a of n is my discrete time signal, what will then be my discrete time Fourier series coefficients. So this I have to find. So first with this, what I'll write it out, I'll write x of n equal to, or I can take the other equation, right? My a of k is going to be equal to 1 over n summation n over n x of n e power minus jk 2 pi by n into n. Now I need to try to bring this to the form of this thing, which with a of n on the left hand side. So what I'll do, I'll replace k with n and n with k. So what I get? A of n equal to 1 over n summation k over n x of k e power minus j n 2 pi over n into k. So this is similar to whatever form I need here, except for a minus sign here, correct? I don't want that minus sign, but I want a of n on the left hand side for sure. So what I'll do, I'll replace k with minus k. Instead of replacing n with minus n. So then what I'll get? A of n is equal to 1 over n. And the summation, it is over any period, right? So if I take from 0 to n minus 1, if I take k equal to minus k, I'll get it from minus of n minus 1 to 0. But this is also a periodic thing, right? Over n summation. So it is going to be equivalent. So these are going to be equivalent. So I can still write summation k over n x of minus k e power j, and I just shuffle them. K into 2 pi over n by n into n. So this is what I want. And if you see, there is 1 by n term here. So I'll just take it inside. So a of n equal to summation k over n 1 by n x of minus k into e power j k 2 pi by n into n. So my discrete time Fourier series coefficient for a of n is going to be 1 by n x of minus k. So 1 by n x of minus k. So this is the duality relationship for discrete time Fourier series. So as an example, you can take this simple case where you have delta of n. So what will be my discrete time Fourier series if you utilize this to find out? So if I substitute delta of n here, only my n equal to 0 term will remain. So I'll get all a k is equal to 1 by n. So my a of k is going to be equal to 1 by n, which is constant. So if I have a constant 1 by n here, which is periodic again with n, even delta of n is going to be periodic. So periodic in n, this also periodic in n. This anyway constant, so it can be periodic in anything. So I'll assume that it is periodic in n. So what will be my discrete time Fourier series here? So according to the relation we had, it should be 1 by n x of minus k. So it is going to be 1 by n delta of minus k, which is nothing but 1 by n delta of k, right? It should be a single pulse. So we'll just check that. So if I substitute 1 by n in the equation here to find my a k's, I'll get 1 by n here. So I'll get 1 by n here, and so that's it, right? 1 by n. Then I have to do the summation over n for this one. And we know this summation is going to be equal to n times, only this summation, right, is going to be equal to n times delta kn. Right, it is only when k is equal to 0, the sum is going to end up at being n. All other cases, it will be 0. So that is why this delta kn. So this n and that 1 by n will cancel, and I will be left with 1 by n delta of kn, which is nothing but my 1 by n delta of k. Okay. So it satisfies our conditions. And hence, if you just know this relation, you can easily find out this relation. That is what it means. You no need to again substitute this and keep finding. So that is where it is helpful. Okay. So even if for some signals this the input signal itself is very difficult and you are unable to sum it up, if you take the Fourier series of it, it may look simpler, right? So then you can solve it in the backward way. You first find the Fourier series for a normal signal, which is easy for you to sum it up. And then you just take the dual of it. That way you can easily find it out. So next, there is also another duality relationship we can find out. If you observe here, if you see this, here is a finite integral and there is a summation here. So within themselves also, there cannot be any duality relationship, right? But if you observe this and this, so here you have an infinite summation, here also you have an infinite summation. Here you have a finite integral, here also you have a finite integral. So we can say that there exists some duality between them. So that is what we will see now. So duality between continuous time Fourier series and discrete time Fourier transform. So first let us write out the synthesis and analysis equation. For the continuous time Fourier series, you have x of t is equal to summation k equal to minus infinity to infinity ak e power jk omega naught t. Again, x of t is going to be periodic, right? And what is the analysis equation? Ak is nothing but 1 over t, t naught integral over t naught, x of t e power minus j k omega naught t dt. So ak is not periodic. Similarly, on the discrete time Fourier transform side, what you have? You have x of n equal to 1 over 2 pi integral over 2 pi, and you have x of e power j omega n d omega, and you have your x of e power j omega equal to summation, let's say n equal to minus infinity to infinity, x of n e power minus j omega n. And again, your x of e power j omega is periodic. And what is the period? Periodic with 2 pi. So if you observe these both equations, this straight away coincide except for a difference of minus sign. And if you observe the other, these two equations, you want your t naught to be equal to 2 pi, and there is also a minus sign difference. So first constraint we'll put is your t naught equal to 2 pi in your continuous time signal x of t. Okay. So even if you have a signal with x of t having period some t naught, you can always scale the signal appropriately, like x of t by a, some constant coefficient, and bring the period to 2 pi, correct? So after you have brought that period to 2 pi, then we will see how the duality relationship exists. So first let me say my x of t has a continuous time Fourier series coefficient a of k. Again, this I am writing for convenience. Then if my a of n is my discrete time signal, what will be my discrete time Fourier transform? So this is what I should find. And again, my x of t is periodic in 2 pi. Already I have written here. So let me take this equation and try to find out. So my a of k is going to be equal to 1 over 2 pi integral over 2 pi x of t e power minus jk omega naught t dt. Right? And what is my omega naught going to be? It is 2 pi by t naught. So it is going to be equal to 1, correct? So first let me write as t naught itself, then do the replacement. So this will be 1 over 2 pi integral over 2 pi x of t e power minus j k t dt. So this is my ak. Now I want to find the discrete time Fourier transform of a of n. So I replace k with n, and t I need to replace it with omega. So I'm aiming for something of this form so that I can find out what my discrete time Fourier transform is. So what I will get, a of n is equal to 1 over 2 pi integral over 2 pi x of omega e power minus j n omega d omega. So this I can replace as minus j omega n. But what form I want? I want plus here. So what should I do? I should either change omega or n to minus omega or minus n. So what will I change? Since a of n is what is my requirement, I will change omega to minus omega. So replacing omega with minus omega. And again my integral will change because this coefficient also will change. But I'll get a minus d omega here, and here let's say if it was 0 to 2 pi, I'll get 0 to minus 2 pi. So then this will become positive and I will be getting minus 2 pi to 0. So that way I am still over a interval of 2 pi, correct? And it is in the increasing order. So my integral will not change its sign and it will remain the same. Okay. So my a of n will be equal to 1 over 2 pi integral still over 2 pi x of minus omega e power j omega n d omega. So is this of the form what I want? So I have 1 over 2 pi and the DTFT of whatever is here, e power j omega n d omega. Okay. So what is my DTFT of A of n? It is gonna be x of minus omega. So this is gonna be x of minus omega. So very simple relationship, right? So I just need to copy down x of t, in just substitute the variable t with omega and just do a simple reversal. So again, let us take an example. So we know our very familiar example. Let me call it, let's say I'll take g of t, okay, is equal to 1 for my mod t less than or equal to t1 and 0 for mod t greater than or equal to t1 less than or equal to pi, because it is 2 pi periodic, right? So this I have. And for my g of t, what is my continuous time Fourier series coefficients? ak, or let me call it gk. Okay, g I have already used, I'll still assume ak only. So what was my ak? It was sine k t1 by k pi. So if I let my t1 to be equal to pi by 2, my ak will be sine k pi by 2 by k pi. Suppose now I want to find the discrete time Fourier transform of this signal. So x of n equal to sine k pi, here it is n. So I'll write pi n by 2 by pi n. So if you straight away try to solve this, you may face some difficulty, right? I want to find the discrete time Fourier transform. But since I have this duality relationship and since I already know this, I can easily find this, right? If my a of k is gonna be here, what will be my discrete time Fourier transform? If I say a of n, it is gonna be g of minus omega, right? And what is my g of t? G of t is nothing but equal to 1 for my mod t less than or equal to pi by 2, 0 for mod t greater than or equal to pi by 2, less than or equal to pi. So g of minus omega, what I have to do, since it is even symmetric, it is same as taking g of omega, right? I just need to replace t with omega. So 1 for mod omega less than or equal to pi by 2 and 0 for omega less than or equal to pi less than or equal to pi by 2. So this is going to be my discrete time Fourier transform. So if I add the signal x of n, how will my g of omega look like, or x of e power j omega will look like? It will look like this, pi by 2 to minus pi by 2, and it is periodic with period 2 pi. So this is the power of duality, okay? So it may not be fully necessary for you to remember all this, but it is good that you should know all these things, okay? Looking for symmetries in any problems only simplifies a solution. So these are the 3 dualities that exist in the Fourier transform and Fourier series. So you can't find any other duality because either the integral will be finite and infinite in the other cases, or your summation will be finite and infinite. So these are the 3 possible dualities. Okay. So next let us look at some basic DTFT pairs. So let us take our signal, our Fourier transform, and if it is for periodic signal, we'll also see the Fourier series coefficients. So first itself we'll see for a periodic signal, if we have some x of t, or here it is n, right? So x of n equal to summation k over n ak e power jk 2 pi by n into n. You know the Fourier series coefficients are ak, then what is your Fourier transform going to be? It is going to be 2 pi summation k equal to minus infinity to infinity ak delta of omega minus 2 pi k by n. And again your ak is also periodic here, correct? Okay. Next let us see for x of n equal to 1. This is again a periodic signal, just that your ak is going to be delta of k kind of thing. So what is your ak? It's nothing but it's equal to 1 for k equal to 0 plus minus n and so on, and 0 otherwise. And here you just need to substitute this thing. So you will get 2 pi into summation L equal to minus infinity to infinity delta of omega minus 2 pi L. So what I have done is I have substituted k with L into n, where L is some integer. So then you will get all these possibilities. Okay. So next let us see e power j omega naught n. So for this my Fourier series coefficient is going to be, so if this omega naught is some 2 pi m by n, then my Fourier series coefficient ak minus m will be equal to this thing. So my ak will be equal to 1 for k equal to plus minus m plus minus m plus minus n and so on. And it will be 0 otherwise. So I'll just get 2 pi summation L equal to minus infinity to infinity delta of omega minus omega naught minus 2 pi L. Right? From the property of Fourier transform, we know if x of n is multiplied by e power j omega naught n, it is nothing but a shift in the frequency domain. Again, this is m plus minus n and so on. Minus n will not come. Similar to 0, right? Okay. So next is your cos omega naught n. Here you will have, this is nothing but 1 by 2 e power j omega naught n plus e power minus j omega naught n. So here your AKs will be nothing but 1 by 2, 0 for k equal to, here if you again take omega naught equal to 2 pi m by n, here only you will have plus minus m plus minus m plus minus n and so on. Because you have both the j omega naught n and e power minus j omega naught n term. So 0 otherwise. So what will be your Fourier transform? It will be pi into summation L equal to minus infinity to infinity delta of omega minus omega naught minus 2 pi L plus delta of omega plus omega naught minus 2 pi L. That's all. Similarly for sine omega naught n, it is 1 by 2j e power j omega naught n minus e power minus j omega naught n. So your AK is going to be equal to 1 by 2j for k equal to m plus minus n, right? And so on. And minus 1 over 2j for k equal to minus m plus minus n and so on. And then 0 otherwise. And what is this going to look like? Pi over j summation L equal to minus infinity to infinity delta of omega minus omega naught minus 2 pi L minus delta of omega plus omega naught minus 2 pi L. Again, it is also sufficient to represent this x of e power j omega over only one period, in which case you will have only delta of omega minus omega naught minus delta of omega plus omega naught. Okay. So next, if you have a periodic impulse given by summation k equal to minus infinity to infinity delta of n minus kn, periodic in n, your ak is going to be 1 by n for all k, right? Then what will be your Fourier transform? It is going to be equal to 2 pi summation k equal to minus infinity to infinity delta of omega minus 2 pi k by n. Here ak will come 1 by n. So since it is constant, I can take it outside. So next let us see for aperiodic signals. The first one will be a power n u of n. And of course my mod a should be less than 1. Otherwise this will have a convergence issue. So for this, we saw it in the example, it was 1 by 1 minus a e power minus j omega. And then if you have a square pulse, let's say your x of n equal to 1 for mod n less than or equal to n1 and 0 for mod n greater than n1. Then your Fourier transform is gonna look like this. Sine of omega into n1 plus half by sine omega by 2. So how will I get this? So with this, my x of e power j omega is nothing but summation n equal to, since it is a aperiodic signal, I'll have minus infinity to infinity x of n e power minus j omega n. So now if I substitute, I'll get summation n equal to minus n1 to n1. It is going to be equal to 1 e power minus j omega n. So this is sum of Gp, which is nothing but a into r power n minus 1 by r minus 1. This is for n terms. So here what is n? N is equal to 2n1 plus 1, because 0 also you have to include. From 1 to n1 there are n1 terms. From minus 1 to minus n1 there are n1 terms. And z plus the 0 ones. So you will have 2n1 plus 1. So and your a is nothing but e power j omega n1, right? You have to substitute minus n1. So e power j omega n1 into e power minus j omega into 2n1 plus 1 minus 1 divided by your r is nothing but e power minus j omega minus 1. So to convert this into sine form, I'll just take half of the term outside. So e power j omega n1 e power minus j omega into 2n1 plus 1 by 2. And here I'll have e power minus j omega into 2n1 plus 1 by 2 minus e power j omega into 2n1 plus 1 by 2 divided by denominator also I'll do the same. E power minus j omega by 2 into e power minus j omega by 2 minus e power minus j omega by 2. Sorry, here it will be plus. So now what I'll do is I'll divide both by minus 2j by minus 2j. So both are give me their respective sign terms. And if I try to add this, I have what I have here, n1 plus half, right? And here I have minus sign. This also gonna be minus. This when I bring it to the top, I'll get plus. And here I already have n1. So this is going to get cancelled overall, totally. So this will give me sine of omega into n1 plus half divided by sine omega by 2. So this is what I have here. Okay, this is for a square pulse, aperiodic signal. So next is what we already saw in this example. So sine omega n by pi n. And I'll also restrict my w between 0 less than w less than pi. So this we already, just now we saw it for pi by 2 case, right? W equal to pi by 2. In general, your x of e power j omega is going to be equal to, again, a filter kind of thing in the frequency domain. So 0 less than or equal to omega less than or equal to w, and 0 for omega greater than or equal to, again, so w less than or equal to omega less than or equal to pi. So again this will be periodic with period of 2 pi. This is a square window in the frequency domain. Okay. So then if you have delta of n, just delta of n without it being periodic, it is going to transform into a constant one in the frequency domain. And if you integrate delta of n, you will get u of n. And you know the integration, the property. If you use that, you will get 1 by 1 minus e power minus j omega plus summation k equal to minus infinity to infinity. The DC term also you will get, which is pi into delta of my omega minus 2 pi k. Okay. And if you just perform a shift for the delta function, you will get e power minus j omega n naught. And then my n plus 1 into e power n u of n. And for mod a less than 1, this is going to have a Fourier transform 1 by 1 minus a e power minus j omega whole square. And again, how do you derive this? You have a power n u of n. This was giving you 1 by 1 minus a e power minus j omega. So n a power n u of n will give you j into d by d omega of this term. If you multiply, what will you get? You will get minus 1 by 1 minus a e power minus j omega whole square into minus a into minus j into e power minus j omega. So how many minus you have? You have 3 minus sign, and also j into j will give you another minus sign. So we'll get plus a e power minus j omega by 1 minus a e power minus j omega whole square. Again, if you add this both, you will, again, this a e power minus j omega will cancel with whatever comes in the numerator, and you will get this term. Okay. So then, similarly, you can extend this to higher orders. It will be n plus r minus 1 factorial by n factorial into r minus 1 factorial a power n u of n mod a less than 1 is going to give you 1 by 1 minus a power minus j omega power r. So these are the basic Fourier transform pairs I wanted to discuss. And our final topic today will be difference equations, right? System characterized by linear constant coefficient difference equations. So in general, for an LTI system with input x of n and output y of n, we have this relation, sum k equal to 0 to n, a k y of n minus k equal to sum L equal to 0 to m, bk or bl x of n minus l. So if we take the discrete time Fourier transform on both sides, you know x of n minus k is going to get transformed into x of e power j omega and an additional term of e power minus j omega k, right? Using that, how will this get transformed? So this I'll put it on the side. So this will get transformed to summation k equal to 0 to n, ak, you will have y of e power j omega, and e power minus j omega k is equal to summation L equal to 0 to m, bl, you will have x of e power j omega, and this will give me e power minus j omega l. So if I want to get the transfer function h of e power j omega, which is nothing but y of e power j omega divided by x of e power j omega, since it does not depend on the summation, I can take this outside. And if I divide, what will I get? Like taking this to the other side and keeping this in the same side. So I'll get summation L equal to 0 to m, bl e power minus j omega l divided by summation k equal to 0 to n, ak e power minus j omega k. So this will be my transfer function. So in my continuous time, I had variables of j omega, but here I am having variables of e power minus j omega. So let us take an example. So if I have my difference equation represented by this, y of n is y of n minus 3 by 4, y of n minus 1 plus 1 by 8, y of n minus 2 is equal to 2x of n. I want to find my h of e power j omega and also h of n. So I'll just take DTFT on this. So what will I get? I'll get y of e power j omega minus 3 by 4 e power minus j omega y of e power j omega plus 1 by 8 e power minus 2 j omega y of e power j omega equal to 2 into x of e power j omega. So my y of e power j omega this side I can take common. I'll get 1 minus 3 by 4 e power minus j omega plus 1 by 8 e power minus 2 j omega is equal to 2x of e power j omega. And my h of e power j omega is nothing but y of e power j omega in by h of x of e power j omega, which is nothing but 2 by 1 minus 3 by 4 e power minus j omega plus 1 by 8 e power minus 2 j omega. So again this denominator I can factorize. So I'll write it as 1 minus 1 by 2 e power minus j omega into 1 minus 1 by 4 e power minus j omega. So if you add them, you will get 3 by 8, and into 2 will give you this term, and if multiplying these both will give me plus 1 by 8. So this again I can split such that my e power j omega minus j omega terms goes away. So 1 minus 1 by 2 e power minus j omega by 1 minus 1 by 4 e power minus j omega. So here I need to have a factor of 2 minus a factor of 1 here. But after the constant term I need to have is 2. But here you will get 2 minus 1 equal to 1. So I'll just multiply both by 2. So I'll have 4 here and 2 here. So this we know, this is nothing but 4 into 1 by 2 power n u of n minus this is 2 into 1 by 4 power n u of n. So this will be my h of n. So this is my h of e power j omega. Right? From h of e power j omega we got impulse response. So this is how you go about finding the impulse response from the given difference equations. And once you have the impulse response and the transfer function, it is easy for you to find y of n or y of e power j omega for any x of n or x of e power j omega. So that is all the theory with respect to discrete time Fourier transform. In the next lecture, we'll solve some questions based on them, and then we'll move ahead. Okay? Okay guys, take care. See you. Until then, bye-bye.